Good afternoon. I'd like to introduce our next session, which is designing an SPE product. Our speaker today is Mark Geisler, who's Senior Manager of Systems and Marketing, Industrial Ethernet for Analog Devices. Welcome.
Hey, thanks a lot. So today we're going to be talking about designing an SPE product, so single pair Ethernet product. We will go over system design considerations, including different types of topologies, microcontroller selection, general block diagrams, and talk a little bit about power and diagnostics around single pair Ethernet. We've been at this show hearing all about the benefits of single pair Ethernet for multiple days now. And in my mind, I think of that as being a number of key features. We're coming from legacy bus architectures like for RS-45 and 4 to 20 milliamperes. With the need for data growing every single day, we have a need for increased bandwidth. So single pair Ethernet will help to enable larger pipes and deliver this information that we need at a faster and larger quantity rate. Single pair Ethernet also reduces system complexity. So it does this by leveraging standardized IP-based security features, common IP protocols, such as Profinet, Ethernet IP, and OPC UA-FX, and it has a benefit of bringing both power and data over that same single pair. This technology also enables both long-reach and multi-drop types of solutions for connectivity, which makes it a great alternative to some of those legacy field buses that can be used in many different ways. Because these are different physical layers, that means there's a need for some education around how these work and the different types of system topologies that can be deployed. Today, we'll talk mostly about 10BASE-T1S and 10BASE-T1L technologies. I think oftentimes people think of 10BASE-T1L as being point-to-point solutions. And they are often unaware that you can actually create daisy chains, lines, and arrays using 10BASE-T1L technology as well, which can enable some very unique use cases we can talk about in the upcoming discussion here. Then there's additionally 10BASE-T1S, which would be multi-drop. And I'm showing this picture here to highlight kind of different types of topologies that are enabled. And I'll expand upon this not fully. So when you've decided that single pair Ethernet is something you will implement in your architectures, you have to be thinking of what types of system topology you will be designing to. So are you a sensor manufacturer? Are you a PLC manufacturer? What type of system are you working in to control the entire system? Then you can choose the types of topologies that you will work in. Oftentimes we see star topologies like in Ethernet HDL type use cases, where single pair Ethernet sensors are operating with the point type fashion. And then as mentioned earlier, you can also do lines and rings with T1L using Ethernet switches and T1L PHYs, or a product that we created at ADI called the ADI-M2111, which is a single chip solution enabling daisy chain lines and rings in a more compact and easy to use form factor. Of course, if you decide that the ring is the way to go, there are some considerations you would need to look into, as you then have to think about the loops that may form. So you probably want to deploy something like MSTP, RS3, or a DLR type solution to account for that. And certainly something that we have helped many with so far and are happy to help others do in the future. So then we get to multi-drop and lines. And I put these on the same slide here to highlight these two different different but similar use cases. Because again, I think oftentimes people think of 10 base 2 technology as being only point to point. It does offer the ability to create those lines of arrays. So if we look at the differences here, T1S being multi-drop, we can operate over at least 25 meters, at least 8 nodes or more. And though, as we heard from our ODVA and Rockwell colleagues earlier this week, there is solutions that have like 40 nodes. Okay? So you can achieve greater than 8 nodes with these types of T1S solutions. Generally, it's half duplex technology, and is generally resistant to some dropped nodes. However, the amount of nodes that you can drop does relate to the type of system that you have. So when you're designing the T1S type of architecture, you have to think of your overall architecture. How is your eye diagram changing, the signal integrity changing essentially as you add more nodes? Each node has a capacitance that you're adding. And so you have to count for that and think of how your system is going to be architected in such a way, potentially even using compensation abductors to enable larger node counts. So if we compare that against T1L, we still support 1 kilometer and greater distances. It's 10 megabits per second, but full duplex in this case. And you can have virtually an unlimited amount of nodes. That's due to the fact that each node acts as a repeater for the signal. Then you can continue having a very good signal integrity throughout your system. The challenge with this type of architecture is that when you lose a node, given that the data is flowing through an Ethernet switch, you have to come up with solutions to enable data and potentially power to continue passing through these nodes. The alternative to that would be to use a ring type architecture, as I mentioned earlier, that would send data either direction so that you could be resilient to a loss of one of these nodes. If we dig a little bit deeper into the daisy chain type of use case, Analog Devices has released an evaluation kit called the ADIN 2111 D1C that highlights how data and power can be transferred on and off the line and through a dead or lost drops. So on the left-hand side of this slide here, we show sort of how this data is working. If the node goes down, there is a relay that actually enables the data to continue flowing through the connectors, even at the loss of operation of that node. If we look at power, like with T1S, there's different ways you can do this, usually an engineered power solution, and that continues also with 10 base T1L. We would have, it's essentially an inductor coupling power on the line and off the line for each node. The key things to consider when power forwarding with 10 base T1L is the location on the cable, the power per node, cable gauge, number of nodes, and the resistance through each node. These all play a factor in that power supply design, the inductor design, product selection. Again, something certainly that we are happy to help with when it comes to making these design choices. So now that you've decided you're going to design a single Ethernet product, you've looked at the types of system architectures that you will either be implementing your design in or adopting. You can think of also location of installation. Is this design being installed in an existing installation, existing infrastructure with existing cabling, or is this a new installation? So you have the benefit of running new cabling, new cabinets. An example of that is like a control cabinet where you would have an entirely greenfield installation. And this will force decisions around how you can pre-qualify those existing retrofit installs and what types of cable selection and system architectures you'll do with a new install. So now you picked your architecture for your device. You've decided where for your system. You've decided where you're going to install it. And you're thinking, how are you going to communicate in that system, right? So this is where industry will make some of these decisions for us. In industrial automation, we see many common protocols being used here, like Ethernet IP, ProBlueNet, Modbus, UA, FX. In the building space, you would hear of .NET IP. But you have to think of those protocols, those stacks. How am I going to acquire that stack? Am I going to buy it? Am I going to build it? Am I going to integrate it? That is often a concern that we see people looking at. It's something that needs to be considered. That choice of both protocol stacks and the acquisition of that stack, or what particular stack it's going to be, will drive both memory and processor requirements. We'll talk about that in processor selection sliding with that. So if we look at the typical device block diagram, so now we moved from the system level down to the block diagram of the device itself. We can see a very busy front end here with a number of different passive components. While it may look scary, they're very simplistic in what they're for. They all serve a purpose here. So we've got ESD diodes or protection capacitors, a common mode choke to reduce the cover of ports. Power would typically, if you're using a power, if you're running power of a single pair, you would typically have typical coupling inductors. And oftentimes we would see data ruffled in with capacitors for either. So let's see. Those resistors shown in this picture are hybrid resistors, and they're there to enable the full duplex features of the T1L PHYs. Those need to be very specific values, which we highlight on our data sheets and app notes. Special note here is that we've just released a product that actually integrates those resistors to reduce the word size and complexity. If doing an intrinsically safe design, you should consider how that affects your design. Do you need those resistors to absorb any energy or service your APL needs in some way? It's something that you would have to consider. So now we take a look at our microcontroller requirements. How is that driven by a link to single pair? The legacy buses using legacy protocols required much less memory. So one of the key things that I see happening here is a need for higher memory density microcontrollers. Memory densities for something like a ProfiNet type of bus memory requirements can be driven up about 2 meg of flash. And so that really does drive your microcontroller selection, because once you start getting up into higher memory density microcontrollers, it starts to limit your selection. We have developed a couple of devices that have been key in that space, like the MAX32690. And then for small UDP operating edge nodes, we have the MAX32672. Or for smaller, lighter protocols, we have a device like that can service those types of edge nodes. You also have to be thinking of your power budget. So for Ethernet APL, do you have a low power microcontroller? Are you prepared for the power requirements that are driven by that use case? So we're powering your device from the super Ethernet line. And then additionally, a topic that we all love, the CRA topic, security. So you need to be thinking, are you compliant to the various regions of the world's cybersecurity standards that are rolling out? You can leverage tools like TLS, OpenSSL, as is shown here on the slide. But you also will need a high level of device security. So this includes secure clue storage, update and authentication types of features. All things that you should be looking at, right? Long gone are the days where you can have a microcontroller with very little security. So now we look at powering that device. As we have discussed earlier, single pair Ethernet allows for SPOE to power these devices. There's a scheme with using SCP stereo communication classification protocol that enables these devices to classify the power device end in have the PSC and the power device talk to each other and allow for known power classes. So these power classes range from 24 volts to 55 volts, and we can deliver up to 52 watts over that single pair. One thing I like to point out is that Ethernet APL and SPOE are different things. So the power requirements are different. With Ethernet APL, you plug it in and it just works. With single pair Ethernet, single pair power over Ethernet or SPOE, sometimes called Twiddle or PODL, you first classify your device at the edge node, and then you turn it on and go. And so these classifications will be different. Here we're showing the chart for the general single pair Ethernet power classes, 2.3 CGs, and also giving an example of cable lengths. So if you're thinking of your edge node, you have to be considerate of how much power you need to draw and what that does to the actual cable lengths that you can achieve. And we've placed some numbers on this slide that contribute some rough idea of the types of power and types of cable that you can run on Anchor and the distances that are achievable. So you've got your system architecture. You've got your board design. You've selected your microcontroller. You know what protocol you want to use. Now you can be thinking of different types of installation challenges you might have. And this is, again, going back to the comment about greenfield versus a brownfield installation. How do you know that existing cable is going to work and that the connections are solid, right? How do you know that there's not a fault at one of the connectors? As my colleague Peter had went over in a presentation earlier this week, there are a number of different types of diagnostic leads in the system, right? There's different types of junction boxes. How do you know that cable is going to be terminated correctly, or there's not a contamination or a short somewhere? Using some type of diagnostic features, and there are multiple ones that we offer, will greatly increase your chances of success. And something you have to be considerate of when you're designing these products. How will I know that they are working correctly? And how will I alert my customer that there is a fault in the system and where that fault is? All right. So wrapping up here. From the concept and the production phases, we have to look at our system as a complete system, both the system architecture, the protocol used, different types of microcontrollers, and our schematics of the actual design itself, and how we're going to power this. Cable testing, being awareness of where we're installing these, and what types of diagnostics we want to deploy. It is also a critical concern. It's something we need to be thinking of from the start of our design. PDI is here to help you along that journey. We've got a collection of not just data and advisements that we can provide, but also a number of evaluation kits and white papers and leadership type articles out on our website that can help you. And I've included some links in this presentation to some of those evaluation kits in this first. So thanks everybody for your time. Is there any questions? Questions? What? Turn right. Thanks a lot.